In this video, we explain the basic structure of a conductive material and the phenomenon of induced charge separation. Then we go on to deduce three key properties of conductors, and our lovely new tool, Gauss's Law, is going to play a crucial role in those arguments. And finally, we'll work an example showing how a conductor reacts if we place a small charge into a cavity within the body of the conductor. So to get started, we can just use this slab of copper as an example. And just a quick review on the structure of matter here. This copper slab is made of copper atoms arranged in a lattice. And we pluck one of these guys out to get a closer look. And an individual copper atom is made of positive nuclei surrounded by a smeared out cloud of negative electrons. And those nuclei are composed of protons and neutrons, where the protons carry a positive charge and the neutrons are, unsurprisingly, neutral. And we're just going to start with a net charge of 0 on our copper slab. In other words, it's electrically neutral. We have the same number of electrons and protons. Now the nuclei and inner electrons are pretty much locked in place in the copper lattice, but what makes copper conductive is that some of the more weakly bound outer electrons are freely shared from atom to atom. This makes the material highly responsive to an external electric field. In other words, if you start pushing on the electrons, they're free to move over large distances. Now, turning on an electric field pointing to the right, we expect our free electrons to wander to the left. And that's just an application of F equals QE, using a negative charge on those electrons, so the electric force points opposite the direction of the electric field. So those electrons are going to pile up on the left side of the conductor. But this material was originally electrically neutral, meaning that the right side of it must now have a deficit of electrons. In other words, it has a net positive charge over there because there are now more protons than electrons in that neighborhood. Now I need to point a couple things out here. First, you might ask why the electrons don't just get ripped off the material and fly to the left. And the quick answer is that it takes a lot of extra energy to do that. We'd need an incredibly strong electric field or another source of energy like a photon impact. So those electrons are just going to hang out on the surface of the conductor over there. Second, I want to point out that we can usually get away with pretending that the positive charges are the ones moving around, even though we know it's actually the electrons. So we would have ended up with the same picture using positive mobile charges, and that's how we usually operate for studying electrostatics and circuits and so on. But you should be aware there are some rare cases like the Hall effect where the sign of the charge carriers actually matters. Now what we're looking at is called induced charge separation. And I want to quickly point out that this induced charge separation creates an electric field of its own. And we'll call that E induced. So electric field points from positive to negative charges, and that's why our induced electric field is pointing to the left. Now, recalling that electric fields add vectorially, we immediately see that the net electric field inside the conductor is at least partially reduced by the induced electric field. But it gets even better than that. We're going to argue that the electric field inside a conductor is exactly 0, provided we're talking about electrostatics. In other words, provided that nothing is moving. And this is actually the first of our three key properties of conductors in electrostatics. The electric field is always exactly 0 inside, provided nothing is moving. And the induced charge separation idea shows us how a conductor might achieve this. If we apply an electric field, charges simply move around to cancel any outside electric field. But here's a slick argument for why the field has to be exactly 0 in a conductor, and we're going to do this by contradiction. So we suppose the electric field isn't 0 at some point inside the conductor. So there we're just looking at some arbitrary location in the conductor, and I'm saying the field just points up and to the right. Well, then we would immediately have charges accelerating in response to that electric force. And wait a minute, we just said it was electrostatics, and that's a contradiction. So having a non-zero field inside our conductor gives us a contradiction. It's simply incompatible with electrostatics, and we conclude that E equals 0 inside a conductor in the electrostatic context. In other words, when charges are not moving, we have a 0 field inside any conductive material. Next, we're claiming that all excess charge on a conductor resides on the surface, and we're going to argue this one by contradiction as well. So we suppose there's an excess charge hanging around in the interior of this conductor. And remember, this thing is chock full of protons and electrons, but those charges are canceling each other out, except for this tiny extra plus Q hanging around in the interior. Well, then we can draw a small Gaussian surface with plus Q at the center and apply Gauss's law. So there's our Gaussian surface centered on the little charge plus Q. And we write down Gauss's law. The integral of E dotted into dA over that surface is equal to the enclosed charge divided by epsilon 0. And of course, the enclosed charge is just Q. And we make all the usual arguments. E is constant over that Gaussian surface. The dot product is trivial because E points perpendicular to the Gaussian surface. This allows us to factor an E out of the integral and then just integrate dA, which is nothing more than the surface area of that Gaussian surface, 4 pi r squared. And we arrive at our usual result for the electric field of a point charge. E is equal to Q over 4 pi epsilon 0 r squared, where r is the distance from the charge. Well, clearly that thing is not a zero electric field. So once again, we've arrived at a contradiction. Any excess charge hanging around on the interior of a conductor produces a non-zero field in its neighborhood. That violates property number 1. And this means in the electrostatic context, we can't have any excess charge hanging around on the interior of a conductor. So if the charge can't be inside the conductor, it must migrate to the surface, giving us property number 2. All excess charge resides on the surface. Incidentally, for this nice spherical conductor, that charge will be uniformly distributed on the surface in order to guarantee a field of 0 inside. Finally, we argue for a third property of conductors in electrostatics. The electric field at the surface must be perpendicular to the surface. And the argument for this one is much like the argument for the first property. We simply imagine an electric field at the surface that isn't perpendicular. So there it is, just pointing off at some wacky angle at the surface of the conductor. And this tilted electric field can be broken into tangential and perpendicular components. So because it's coming off at some wacky angle, it has a component parallel to the surface of the conductor. And that parallel component, that's going to cause electrons to accelerate along the surface of the conductor. And again, we have a contradiction. So if the setting is static, in other words, nothing is moving, then the electric field must point perpendicular to that surface. Now remember, E isn't going to rip electrons off the conductor unless it's extremely strong. So we aren't worried about that possibility for the perpendicular field. The charges are just stuck there at the surface. Okay, so those are our 3 key properties of conductors. E is equal to 0 inside, all excess charge resides on the surface, and E is perpendicular to the material at the surface. Let's put our properties to use in a quick example. So in our example, we have a spherical conductor with a cavity hollowed out of it. And we've placed a little charge of plus Q at the center of that cavity. And I've clearly placed the cavity off center just as a generalization here. And our challenge is to describe the distribution of charge for this conductor and the electric field in all regions. So let's just start by noting that we know E has to be 0 inside the conductive material itself. And now we'll go ahead and start inside the cavity. We have a little plus Q isolated there at the center of this cavity, and we can surround that guy with a Gaussian surface. So we apply Gauss's law along that Gaussian surface. That's the integral of E dotted into dA is Q enclosed over epsilon 0. And because that surface is centered on plus Q, we'll have a constant field magnitude along the surface. And the dot product is trivial because the electric field is perpendicular to the Gaussian surface. So all this familiar stuff happens. The dot product is trivial. We can factor the E out of the integral. When we take the integral, we get 4 pi r squared. That's the integral of dA, or just the area of the Gaussian surface. Our charge was called plus Q. And we find the usual field of a point charge inside that cavity. So that's Q over 4 pi epsilon 0 r squared, where r is the distance from the center of the cavity where plus Q is located. So just drawing that into the picture, there's our usual point charge field emanating from the plus Q. So what about outside the cavity? Remember, we're guaranteed the electric field is 0 everywhere outside the cavity. And the only way this can occur is if a negative charge of minus Q swarms over this inner surface to shield the conductor from the electric field. So there's a minus Q that's now swarmed on the inner surface of the cavity. There just wasn't room to put the minus signs on the inner surface there. And this guarantees the field is going to be 0 outside that cavity. Now to put this on firmer mathematical footing, what we're really doing is applying Gauss's law again. So there's a Gaussian surface that contains our cavity. And now we write down Gauss's law. But this time, the net enclosed charge inside that Gaussian surface is 0 because I have a plus q at the center of the cavity and a minus q that is swarmed onto the surface surrounding that. So with the integral of E dotted into dA being 0, we can conclude the electric field is 0 as well. So next, we realize that having a bunch of negative charge swarm onto this cavity means there's excess positive charge left over. And of course, that excess charge must reside at the surface, on the outer surface of the conductor. Because of the spherical symmetry of this thing, that charge will be uniformly distributed over the surface to guarantee that E remains 0 inside the conductor. And we remember that electric field points away from positive charges, and that the electric field is guaranteed to be perpendicular to this outer surface. So there's what the field vectors look like at the surface of our conductor. And finally, to get just a little more detail, we apply Gauss's law one more time. So we're going to take a Gaussian surface just outside our spherical conductor, and we write down Gauss's law, the integral of E dotted into dA is Q enclosed over epsilon 0. And note here that the net enclosed charge is just plus Q. So we have a plus Q inside the cavity, but that's canceled out by a minus Q that swarmed onto the surface of the cavity. And then we have a leftover plus Q at the surface of the conductor. So our net enclosed charge is just Q. Of course, our electric field is perpendicular to the Gaussian surface, rendering the dot product trivial. And the symmetry of the problem implies that the magnitude of the electric field is the same over the entire Gaussian surface. So on the left-hand side, all the usual things happen. We get E times 4 pi r squared. And on the right-hand side, again, our net enclosed charge is just Q. So we get a Q over epsilon 0. And we solve for E again. And we find our usual point charge field, Q over 4 pi epsilon 0 r squared, where r is now the distance from the center of our conductive sphere. So if we're measuring the electric field outside this conductive body, the electric field is identical to the field of a point charge located at the center of the conductor. We actually can't tell that this originates from an off-center cavity with a plus Q inside with a swarm of negative charge around the outside of it. We're just back to that simple point charge field. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Gauss Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Gauss Lab, and best of luck on your math and physics journey.